Hi everyone. Today we're going to look at a few of the different careers in engineering and engineering technology. To begin, let me start by asking you a few simple questions. First, are you a problem solver? Are you curious about how things work? Do you enjoy looking for ways to make things better and even more efficient? If you answered yes to any of these questions, then you should really start considering a career in a field of engineering. Part of my goal for this class is to provide you with some exposure to the many different subfields of engineering that are available to you once you graduate from high school. To seek employment as an engineer, you're going to need to earn a Bachelor of Science degree from a college or university. This degree could take 4 to even 5 years to complete, depending on where you choose to study. When you get a chance, spend some time researching which college is going to be right for you. If you get the opportunity to visit any of the schools, I would encourage you to ask some of the engineering students why they were pursuing a degree in engineering and what made them choose that school that they're currently attending. Keep in mind that after you receive your degree, you'll most likely do one of two things. You might enter the workforce within your area of specialization, or you might pursue a secondary degree in that specialization. In many states, a test is required for you to become a licensed engineer. Some colleges offer a co-op or work-study program. These programs give students valuable real-world experience that can be helpful in landing their first career job. Many times, a student co-op leads to a full-time job. Go ahead and take a few minutes to watch this video that discusses the future of engineering. Within this presentation, we'll define what is engineering, we'll discuss the difference between engineering and engineering technology, we'll also identify various accredited engineering programs that are available to you, and we'll finally highlight the many different engineering disciplines that you could potentially look at as a future career choice. So what exactly is engineering? Well, an engineer is someone who applies their knowledge of science and math to solve a variety of problems. Many people confuse the work of engineers with the work of scientists. As a student of engineering, you should learn how to define these separate disciplines. An easy way to do that is to think of it like this. Scientists ask and answer questions, discovering new knowledge about how the world works. Engineers use that knowledge that the scientists discovered to solve problems and create technologies that satisfy human wants and needs. If you aren't sure which colleges or universities provide quality engineering programs, then this is the slide for you. Quality engineering programs are accredited through the Accreditation Board of Engineering and Technology and is commonly referred to as ABET. This is an organization that helps standardize requirements among colleges and universities. Currently, ABET has accredited over 2,800 different programs at more than 600 colleges and universities. Take some time to pause this video and visit www.abet.org to learn more about the courses of study and the ABET accredited institutions. Throughout history, engineers have improved the quality of life by designing systems for supplying clean water, developing genetically modified crops, and creating better medicines and medical procedures along the way. By improving the human condition, engineers play a vital role in our society. Let's take a look at 17 important engineering disciplines and the kind of education and training that you would need in order to become these types of engineers. As you can see on the slide, here are the 17 engineering disciplines that are listed in alphabetical order. These include aerospace, agricultural, biomedical, chemical, civil, computer hardware, electrical, electronics, environmental, health and safety, industrial, marine and ocean, materials, mechanical, mining and geological, nuclear, and petroleum. For each of these remaining slides in this presentation, make sure you click on the title of each engineering discipline in order to learn more about each of them, including a summary of what they do, the work environment, how to become one, the average pay, the job outlook, similar occupations, and much more. As you study engineering principles and their applications, you'll discover that engineers have many different career paths that lead to a wide variety of engineering disciplines. The major engineering categories are civil, electrical, chemical, and mechanical. These disciplines are so broad that some engineers pursue a specialty within that category, while others blend two categories together. For example, aerospace engineering is considered a subcategory of mechanical engineering, whereas an industrial engineer blends both electrical and mechanical disciplines together. Watch this video to see how different disciplines in engineering work together to create a vending machine. Aerospace engineering is concerned with engineering applications in the area of aeronautics, which is the science of air flight, as well as astronautics, which is the science of space flight. Aerospace engineering deals with flight of every kind: balloon flight, sailplanes, propeller and jet-powered aircraft, missiles, rockets, and even satellites, as well as advanced interplanetary concepts such as ion propulsion rockets and solar wind vehicles. Aerospace engineering will be responsible for making future interplanetary travel possible. The challenge is to produce vehicles that can traverse the long distances of space in shorter periods of time. New propulsion systems will require that engineers venture into areas that were never once before imagined. At the turn of the 20th century, a large majority of the working population was engaged in agriculture. As farming efficiency increased and people left farming for jobs in the industry, fewer farmers were needed. Contemporary farmers are able to feed about 10 times as many families as their ancestors did over 100 years ago. Today, less than 5% of the U.S. population works on farms. How are fewer farmers able to feed a larger population? The application of new technologies and engineering to agricultural practices have vastly increased farmers' efficiency as well as their productivity. Agricultural engineers design machinery to plant, fertilize, and harvest food crops. They design structures for crop storage and develop methods to conserve soil and water. They even produce new seeds and plants that are genetically engineered to improve crop resiliency and even to resist pests. Biomedical engineering is also referred to as bioengineering, which is a multidisciplinary STEM field that combines both biology and engineering together, applying engineering principles and materials to both medicine and healthcare. The increasing demand for biomedical engineers is linked to society's general shift towards everyday utilization of both machinery and technology throughout all aspects of life. The combination of engineering principles with biological knowledge to address medical needs has contributed to the development of revolutionary and life-saving concepts such as artificial organs, surgical robots, advanced prosthetics, new pharmaceutical drugs, and even kidney dialysis. Chemistry has been studied for centuries. However, chemical engineering began its rise to prominence shortly after World War I. Chemical engineering uses the science of chemistry to change the composition or properties of materials and make them more useful for industrial processes. Chemical engineers are involved in manufacturing of polymers, drugs, paints, pesticides, cosmetics, and even food. They even work in oil refining, paper products, and textile manufacturing, and the extraction of metals from ores. Many specialty areas within chemical engineering are growing very rapidly. Civil engineers provide communities with structures such as buildings, bridges, dams, and roads. Civil engineers are concerned with planning, designing, and supervising the construction of structures. Consider the challenges that civil engineers face as they have to design and build structures that can withstand earthquakes and even extreme weather. Today, civil engineers focus on structures and structural systems such as bridges, skyscrapers, tunnels, canals, transit systems, highway systems, recreational facilities, industrial plants, dams, nuclear power plants, railroad lines, harbors, and even offshore oil and gas facilities. When civil engineers improve the movement of people on roadways, they also are protecting the society as well as its environment. Reducing traffic can reduce toxic emissions from individual vehicles, and improvements in highway design systems can minimize the number of accidents. The civil engineer is always at the center of discussions when municipalities are planning new buildings and transportation systems. Large, medium, and small organizations alike all depend on computers to manage inventories, create invoices, record sales, and communicate with their customers. The amount of data storage possible makes the computer virtually indispensable. Computers of the past were the size of a room. Today's computers have been downsized to the size of your fist, with computing speeds that were unthinkable just a few years ago. The world has become almost completely computer-centered, and the computer's roles should only increase thanks to the engineers who focus their efforts on the research, design, and testing of computer hardware components. Electrical engineers solve problems using electrical principles. These principles are relatively new to us. George Ohm and Michael Faraday were only beginning to build our understanding of the science back in the 19th century. Our first electrical engineers included inventors such as Thomas Edison, who supplied DC to New York City residents back in 1882. Imagine how many alterations there had to have been to take us from the first electronic television using cathode ray tubes in 1931 to today's new, modern, and improved TVs. Every household gadget practically has been transformed by electrical engineers. Today, electrical engineers might design an effective radar system, they might determine new ways to harness electrical power, they could even test aircraft electrical equipment, or just oversee electric utilities. Electronic engineers create and maintain electronics using computing, aviation, manufacturing, communication satellites, and many other different types of technologies. They often work for corporations, the military, medical companies, and scientific organizations. These professionals design new electronic systems, test the equipment, and make modifications to existing systems. Environmental engineering is the branch of engineering that's concerned with protecting people from the effects of adverse environmental effects, such as pollution, as well as improving environmental quality. Environmental engineers work to improve recycling, waste disposal, public health, and water and air pollution control. The most important role of a health and safety engineer is to develop procedures and safety standards for a workforce to follow in order to ensure a safe and productive work environment. These engineers are vital in that they leverage their existing knowledge in the field to develop streamlined processes to ensure workers do not get sick or even injured by their work environment. A health and safety engineer would generally review new equipment workers may be using soon and ensure that it can be operated safely in the work environment. They would also inspect a facility for hazardous conditions. They want to ensure that the work environment is safe, safety gear is being worn and utilized properly, and that equipment is properly maintained and safe to use at all times. Based on their observations, they would recommend additional safety measures and process improvements. For example, they may add a new safety device on a machine or educate the workforce on the proper use of safety gear and implement new safety and health policies. If there's a work-related accident, a health and safety engineer would review the reports and may even conduct additional research, such as interviews, in order to reduce and hopefully eliminate the accident from ever happening again. Industrial engineering is a growing branch of the engineering family. Industrial engineers study engineering principles and techniques that can help make manufacturing processes more efficient and even more profitable. These innovators are skilled at finding ways to do more with less. Their efforts can help improve customer service and product quality, making workplaces safer and make the work even easier. Industrial engineers must design, install, and improve systems that help integrate people, materials, and equipment to efficiently produce certain goods. They must coordinate their understanding of the physical and social sciences with the activities of workers in order to design areas in which all workers can produce the best results. Marine and ocean engineering is another multidisciplinary engineering field that's aimed at solving engineering problems related to the ocean environment, where engineers can help oceanographers wisely explore the many vast oceans. They design and build structures, equipment, and instruments that help advance marine science. They may help in even building ships, aircraft carriers, submarines, sailboats, oil rigs, underwater robots, and acoustic sonar technology. There's a huge variety of things for ocean engineers to do these days. New materials have been among the greatest achievements of every age, and they've been central to the growth, prosperity, security, and quality of life of humans since the beginning of history. It is always new materials that open the door to new technologies, whether they're in civil, chemical, construction, aeronautical, agricultural, mechanical, biomedical, or even electrical engineering. Material scientists and engineers continue to be at the forefront of all of these and many other areas of science as well. Material science and engineering influences our lives each time we buy or use a new device, machine, or structure. The role of a materials engineer is to figure out what ingredients should be used to create a product and to figure out how to make that product with those particular ingredients. Experience shows that all of the useful properties of a material are intimately related to its structure at all levels, including which atoms are present, how the atoms are joined, and how groups of atoms are arranged throughout the material. Most importantly, we learn how the structure and the resulting properties are controlled by the processing of a material. A material may be chosen for its strength, its electrical properties, resistance to heat or corrosion, or a host of other different reasons, but they all relate to its properties. Material engineers can work in nearly any industry, ranging from cosmetics to even appliances. Automobiles, engines, heating and air conditioning systems, gas and steam turbines, air and space vehicles, trains, ships, servo mechanisms, transmission mechanisms, radiators, mechatronics, and pumps are a few of the systems and devices that require knowledge of mechanical engineering. Mechanical engineering deals with power, its generation, as well as its application. Power affects the rate of change or motion of something. This can be a change in temperature or a change in motion because of an outside stimulus. Mechanical engineers use this knowledge of how things move to accomplish a variety of tasks. The vast amount of studying required to become a mechanical engineer allows students to diversify into many other different types of engineering disciplines. The major specialty areas of mechanical engineering include applied mechanics, control, design, engines and power plants, energy, fluids, lubrication, materials, pressure vessels and piping, transportation and aerospace, and heating, ventilation, and air conditioning, which is known as HVAC. A mining and geological engineer is someone who designs mines for safe and efficient removal of minerals such as coal and metals for manufacturing and utilities. Mining engineers work mostly in mining operations in remote locations. However, some work in sand and gravel operations located near large cities. Mining and geological engineers often specialize in one particular mineral or metal, such as coal or gold. They typically design and develop mines and determine the best ways to extract metal or minerals to get the most out of those deposits. Some engineers work with geologists to find and evaluate new deposits. Other mining engineers develop new equipment or direct mineral processing operations to help separate minerals from the dirt, rock, as well as any other materials. Mining and geological engineers use methods grounded in their knowledge of geology to search for mineral deposits and evaluate possible sites. Once a site is identified, they plan how the metals or minerals will be extracted in an efficient and environmentally sound way. A nuclear engineer researches and develops the processes, instruments, and systems used to get benefits from nuclear energy and radiation. Many of these engineers find industrial and medical uses for radioactive materials. For example, in equipment used in medical diagnosis and treatment. Nuclear engineers are also on the forefront of developing uses of nuclear material for medical imaging devices. They may also develop or design cyclotrons that produce a high energy beam that the healthcare industry can use to treat cancerous tumors. Petroleum engineering deals with the exploration, extraction, and production of both oil and natural gas. A petroleum engineer is also known as a gas engineer, determines the most efficient ways to drill for and extract the oil and natural gas from any particular well. They also oversee the drilling operations and are expected to resolve any operating problems. Petroleum engineers usually specialize in a particular aspect of drilling operations. For example, a reservoir engineer determines the best way to recover the most oil or gas from a particular deposit, and they estimate how much that will be. Drilling engineers figure out the best way to drill a particular well so that it's economically efficient and safe for people as well as the environment. Completions engineers decide the best way to finish building a well so that the oil or gas flows upwards from the ground. Production engineers monitor production and figure out how to coax more out of underproducing wells. Petroleum engineers are so vital to today's economies. They make the drilling processes safer for people, communities, wildlife, as well as the environment. They also make it more efficient and prices more affordable to its consumers. They ensure compliance with best practices, industry standards, and environmental and safety regulations. As we continue to study the various engineering disciplines, I want you guys to start thinking about whether your career interest is going to be focused more in engineering or engineering technology. The distinction between engineering and engineering technology primarily comes from the differences in their educational programs. Engineering undergraduate programs are going to include more mathematical work and higher level mathematics than technology programs. Engineering undergraduate programs often focus on theory, while technology programs often focus on application. Once you enter the workforce, engineering graduates typically spend their time planning, while engineering technology graduates spend their time making plans work. So to kind of summarize this, the work of engineering technologists focus on the applied and practical applications of engineering principles, where the work of an engineer emphasizes the theoretical aspects of mathematical, scientific, and engineering principles. Hope this helps.